Hello, what is up everybody? Welcome to CS 302 Online Video 5. Hope you all had a good weekend. Today we're going to keep talking about recurrence relations, which we left off at the end of last week. So, last week, to do a quick review of what we did, we show you two different methods to basically go over these recurrence relations. So, here, let me zoom out a little bit more. We sort of did like from the inside out, or from the top side down, and then from the downside up, right? So one of the ways that we did it was we had the base case, and we have, remember, recurrence relations have two cases, the recursive case and the base case, just like regular recursion. And so we said, okay, what if we start out from the bottom, so from the base case, and from that base case we build sort of the next case, T1, and then T2, and then T3, and then we kind of extrapolate that all the way to Tn, and then make sort of a guess as to what it could be, and then prove it by induction, basically. The other way that we did it is from the Tn down to the T1. So we said, okay, from Tn we can solve what Tn minus 1 is, Tn minus 2, and then eventually we can sort of stretch that out all the way to T0, and then kind of cancel out the terms, which is what we did down here. And come up with the final solution, essentially, which in this case was Tn minus, I think, T0 or something, this one. So just two different ways, and we're going to kind of do more examples of that, and then I'm going to show you going from Tn to T0, so Tn minus 1, T minus 2, but for a little bit more complicated one as well. But before that, I want to do a quick review on logarithms. So I really should have added here log review. There we go, logarithm review, because we want to start looking at some of these different recurrence relations that are not just like plus 1 minus 1 times 2 or divided by 2. We want to look at logarithmic stuff, because there's a lot of algorithms whose asymptotic complexity is in the logarithmic range. And so first of all, let's clarify something about what we mean when we talk about logarithms, okay? And we have viewers. Okay, cool. So you guys are here. Good. So when we talk about logarithms, if you ask a math person, you know, if I go ahead and put something here that says log of n, if you ask a math person what this means, like a math person, they're going to tell you that when they see the word log, they're probably referring to log e, or base e, which is typically represented as the natural log. So if you just tell them logarithm of something, like logarithm of 5, they're going to be like logarithm base e. Okay, so this is the math people. If you ask somebody in physics, and you tell them again log n, what are they going to think? Well, they're probably going to be thinking base 10 n. Okay? That's what they would be thinking. Because typically when they're talking about in physics, they usually use a base 10 logarithm. That's okay. However, we are CS people, right? And CS people, when you see the word log n, we are not talking about base e. We're not talking about base 10. If we're just saying log, we are more than likely talking about, wait for it. What do you guys think? What do we love? We love binary, right? So we typically talk about log base 2. So whenever you see in this class something of the form, there you are, base 2, something of the form like log n, or log 2n, or even just like log 5 or log a, if you don't see me put a base to these logs, because logarithms always need a base, then you can make a safe assumption that we are talking about base of 2. Okay? So log base 2. So for those of you that haven't used logs in a while, what is that equal to? This can be rewritten as let's say log equals x, 3. You're right. So this can be written as 2 to the power of x is equal to 8. So essentially what a logarithm is asking is, what number do I need to take, what power of 2 do I need to take to get 8, essentially? And in this case, the answer is indeed 3. So x is equal to 3. Because 2 to the power of 3 is 2 times 2 times 2, which is equal to 8. So when you see a log, something like log 8, that means that you're saying, to what power do I need to raise 2 to get 8? And that is why it's important to know what base we're talking about. Because if you were asking this same thing to somebody in physics and they would assume to be a base 10, then this would actually be less than 1, right? It would be, because 10 to the power of 1 is already 10, which is bigger than 8. So this would be something like, I don't know, 0.8 or 0.9, something like that. So essentially, it matters. The base matters. So just remember, in this class, whenever you're talking about logarithms and you see in the book or anywhere online, typically with CS-related stuff, asymptotic complexities of algorithms, it is always talking about base 2. Okay? Unless, of course, you explicitly put it. So like here, I am explicitly putting the base 2 there. But if you just see me put something like this, then you can safely assume that this is talking about base 2, in which case the answer to this would be 4, because 2 to the power of 4 is 16. Now, what happens if the number here was like 15? Well, there's some algorithms that you can figure this out by hand, but in this case, I'm just, you just kind of guesstimate, because you know that 2 to the 3 is 8, and 2 to the 4 is 16, and since this is kind of close to 16 but less than 16, then this would be somewhere like 3.9 or something. But you can always go on Google and figure out what that is, or write a little program that solves it for you. Okay, so that's your logarithm review. However, I would like to also bring up a couple of logarithm properties that may come in useful when we're solving recurrence relations and other exponent stuff. So, for example, some of the most basic ones, but it's still good to have them refreshed. If you have something of this form, x to the power of a times x to the power of b, this can be rewritten as x plus a to the power of a plus b. Okay, so like 2 to the third power times 2 to the first power is the same thing as 2 to the fourth power. Okay, whenever you're kind of stuck with some of these, it might make sense to just plug in some numbers and kind of see by example that it works. Now, that is not an exhaustive proof if you're proving something, but at least to prove to yourself, it's enough. Only time that examples can be used as proof is when you're actually doing it for counterexamples. So when you're proving by counterexample, that is a legitimate thing. But you can't prove something by example because that example doesn't necessarily mean that it extends to all cases. And if it did, then what you'd be doing would be a proof by induction. Okay, so another one is the kind of the opposite of this, which is with division. So xa divided by xb, the same thing as xa minus b. That's a useful one to know. By the way, x to the power of 0 is always 1. So no matter what number you put to the power of 0, you're always going to get 1 out of that. And then I guess x to the power of 1, I'll put that one too, is always equal to x. Okay. Let's see. I have a couple written down here, but I'm thinking of more. If you have something of this form with exponents, like x to the power of a and then y to the power of a, then you can take out the power of a with parentheses and put it outside like that. And then the division version of that would be that one I have here. It's just that. Okay. For square roots, or actually, well, first of all, if you see something like this in a power, you can, the good way to do this is just to split it. You can split the division part from the multiplication part, or if you prefer to work with square roots or just roots in general, then you can put it in this format. Okay, so basically, when you see like x to the half power, that is the same thing as saying like the square root. So like this is the same thing as saying square root of x. And technically speaking, any root. So like, that would be the cube root. Okay? So that's just, the 8 to c to b is just like the extended case of that. So, also, a cool thing you can do here with this one is you can convert that one to say that, and then you can take the c out like that. I believe you can do that as well. Yeah. So that could, these things are going to be useful for us when we're trying to simplify stuff. You can also, I suppose, put it in this format. Although that one you don't really use often, but I guess it's good to know. Okay, now moving on to logarithms. So these are actually going to be very critical in a few minutes here. If you have a logarithm that is made up of this, so like let's say log 8, you can split log 8 into like log of 2 times 4, right? And that can basically become log of 2 plus log of 4. We know log of 8 is equal to 3, right? Log of 2 is just 2 to the power of 1 is 2, so just 1. And then 2 to the power of 2 is 4, so 2. So this is equal to 1 and it's equal to 2. 1 plus 2 is equal to 3, which is the same thing as log of 8. So there you go, you can see that. So that actually extends in general to log of b of x plus log of b of y. Okay, and again here, even if it's the base doesn't matter, it'll extend for anything. One that I just remembered, when you see asymptotic complexities, and we said, like, for example, it goes from constant, and you got n. Well, before n, actually, sorry, you have log n. You also have square root of n. Then you have n and then squared and so on, right? Well, I was claiming, and I showed you, I think, but I'll show you again, that log of n is the same asymptotic complexity as square root of n. That's because with log base 2 of n, it turns out that it is indeed the same. Because essentially what you can do here is this is equal to n to the half, right? And if you take the log, then you will see that aside from potential constant, they're going to be identical. So that I think I showed that last week. No, the week before that. So yeah, that pretty much the same thing. The property that you can use, I am going to show you next. So, I guess before I show you that one, let me show you the minus version of this, I suppose, and I'll show you that. So this one, you can do the same thing if you're dividing like that. That can become log b of x minus log b of y. So there's that one. Okay, so anyway, the way that you can prove the one right here, so the way you can prove this is there's this property that is log b of x to the n. You can take that exponent down here, and this basically becomes n log bx. So the exponent inside of the log, you can take it out as just a multiplier, basically. Okay? And so if we look at this now, you know, what we're doing here is we can take the log of it. You know, we can take the log of this, log n to the 1/2, and then just bring down that exponent out here, like that. And there you go. Okay? So, yeah, I'm going to get rid of this, though, because I don't want to mess with the properties here. But it is important to know that, yes, they are indeed equal because of the special case that it's a base 2, okay? Other ones, well, I guess some base ones, which is kind of like the flip of the exponents. The log of 1 is always 0, and the log of itself is always 1, like log 2 is 1. This one's, this one uses another property. So here, log bb to the power of x is always equal to x. Now, this one, I'll let you think for a second as to the why, but what we're basically using is, okay, I waited a second. This one, you're bringing down the x down here, and then log bb is just equal to 1. So, you know, what you're doing here is you're taking the exponent down here, so that takes care of the exponent, and then this is like log 2, which is basically just 1. So this just becomes x times 1. Okay? This one I don't remember actually as to the why it works, but I'm going to write it down here for a second. Log bx is equal to x. So that one I have to actually think for a second. So this one says b to the power of log bx is just equal to x. I don't remember as to the why that is true. I'm trying to think how that works. First of all, let me make that x nicer. Oh, I think maybe I can figure it out. So I think if we take the log of both sides, yeah. So let's try that. So if we take the log of this side, which means we have to take, you know, the log of that side or whatever. The point is then I can bring down the entire exponent here. And this just stays a 1 there. Right? Oh, no, not even the 1, just b. At which point, then I can bring down the exponent from here down. And then this here is a 1. So from there, we know that log b1 is 0, but that would cancel out. So that would just, everything would just become 0. Oof. I'm not sure. I'm not sure about that one as to the why it works, but it works because it just works. So I will leave that one as an exercise to you to figure out as to the why that is true. But I know that it's true. So okay. Moving on. We have log AB is equal to 1 over log. Oh yeah, this one's really cool. You can flip the two numbers here, the a and the b, the two variables, by dividing everything. I wonder if we could use that one for the one that we just did. You know, there's definitely a relationship on this previous one between the fact that this base is the same as that. Let's try it. See, I don't like just kind of putting something and not explaining it. Let's try it with numbers. Let's say that we put a 2. 2 to the log 2 of 8 is equal to 3, right? Or 8, sorry. It makes sense if you plug in numbers, like, because the same number that you're getting from here, which, you know, this would be 3, you're going to take the exponent again. So it makes sense with numbers, but I can't tell you mathematically why. I can't simplify mathematically because I don't remember how to. But you can see that it makes sense. Like, you're taking the logarithm and then you're basically undoing that by taking that number again to the power of it. Do you guys see that? So like log 2 of a number is going to give you whatever 2 to the power of something would give you that number. And then by taking that same number, which is the 2 the base, and then taking it to the power, you're undoing what the logarithm is doing. So it's like canceling each other out. So yeah, in fact, I would like to propose that you can probably chain this into like a really long chain of like powers. So I could say something like b to the log of b of x, and then take that whole thing, which is equal to 8, and then take the log of all of that with respect to b, and then put that there like that. So like I could chain that and that should still all be equal to basically x, right? Because we know that the inner part is going to be equal to, if we plug in the numbers up here, it's going to be equal to 8. And then we take again the log of that, which is equal to 3. And then we take it to the power of 8, right? So that's like saying 2 log 2. And then here we got 2 log 2 8, right? So this whole thing, we know the inner part because we used it is equal to 8. So then that simplifies to 2 log 2 8, which yet again is 3, and then 2 to the third is 8. So yeah, so you could like chain this forever if you want to, just to make somebody's life complicated. And then have this whole thing like that, So it could go on forever, and it would always work. It's like kind of like how you can cancel the address off operator with the dereference operator. So maybe you could, but that is not how I want to spend my day doing that proof. But yeah, but anyways, at least now I feel better because now you kind of see that it works, even though the math is like there must be simple math, but I just can't think of it right now because if we can see it with basic numbers that it works, I'm sure that the mathematical proof is like not that fancy. But yeah, anyways, I'm gonna shrink this down so that so it doesn't get confused with the other stuff. But anyways, all right, so now I feel better about that than just being like, yeah, guys, this just believe. Sometimes you have to believe for some of these things. I mean, I'm not gonna lie. Some of the algorithms are like magic, but yeah. Okay, so this one with the flipping, probably magic too, actually, but it works. No, the way you got to do this one is you have to you got to take the log of both sides again and divide, and you're kind of using the idea of like when you're doing an exponent with a fraction, it's the same thing as a square root. So yeah, it's a lot easier to see that with the one beneath it here too. This can be converted into log. You can create a common base like this, and that top one's sort of a special case for when the base is the same. Yeah, so like if you pick C to be the same thing as B, then this basically becomes the same thing as this. And so you have that sort of common case. So I'll write it because I feel like otherwise you'll be confused. If I make C equal to B in this scenario here, then this one all of a sudden is very clear. Because, this basically becomes log AB is equal to log, and then because C is equal to B, this becomes BB. And then down here, this becomes, instead of CA, becomes BA. Log BB, we saw, is like 2 to the 2, so it's just 1. So this just becomes a 1. So this is the same thing as here. So we know how to get this from the one beneath. Now, as to the one beneath works, that one is the one that's kind of like magic, because you have to kind of figure out how logarithms work for that. It's kind of like dividing both sides by the same value essentially, but even then, this was also kind of magic. But again, if you plug in numbers, it works. So yes, I'll stop at that one. I think that's the last one that I have. Yes. So anyways, the reason why I'm writing all these down is because technically speaking, the test is open notes. So if you happen to run into any of these and any of the recurrence relations in the test or in your life, they can be useful. We're gonna use like one of them today, I think, or two. But they're always good to know because they can simplify your problems. And that's the whole purpose of doing these things, is to not to make your life harder, but to make it easier by simplifying the math. So anyways, that's our logarithm refresher. I will refer to your math people for your math professors for more details about that. So going back to the topic of the day, recurrence relations. I have a recurrence relation here that we're going to solve, or we're going to attempt to solve, and hopefully we solve it. And that is T of n is equal to 2t, I hole punched it right at the spot. Okay, n divided by 2. Yeah, that's it. N divided by 2. I don't like writing it like that. Let me write it like this. It'll take less space. Plus 4n. Okay, as you can see, this is already a little bit more fancy than our whole tn is equal to tn minus 1 or whatever. We have a division. We have multiplication on it. We have like numbers. They're still very basic numbers, but they're numbers. Okay? And I suppose I should include the base case. Our base case is going to be t of 1 is equal to 4. Okay? So that's what we got. And what we're going to do is we are going to try to solve this from the end to the beginning. So we're going to figure out what, like, in this case, not necessarily n minus 1 is, because it turns out that the next term here is not n minus 1. Because what's the recursive part say there? It says n divided by 2. So this one, already you can see that the size of n is not shrinking necessarily linearly. It's getting divided by half already. Already there, like, your logarithm senses should be tingling, other than the fact that we spent like the last 10 minutes doing logarithms. But they should already kind of be tingling, you know, like, hey, this is definitely not linear. And so you will be correct in that sense that it is definitely not linear. So, and we do have the 4n over here. That is going to play a role. But already you can see that this is a little bit harder than before. Okay, so the method we're going to use today is still going, like, again, from the end to the beginning, but it's going to be a little bit different. This is what is known as the build and expand method. Okay, it's kind of, we already kind of did it, but this is a little bit more formalized way of doing it, and it will work better for more complicated problems. Okay, I mean, and I think this is about as hard as we're going to do with these. You will do harder ones in math classes, but I think, yeah, I will still show you the Master Theorem for harder ones if we have time. But yeah, so this was like the peak difficulty of this class of recurrence relations. Okay, so the way we're going to, I'm going to zoom in here. I'm actually going to, I don't like the page divider there, so I'm going to bring my recurrence relation. I'm actually going to make it all in one line like that, and then I'm going to bring it down to the next page. Okay, and so now what I'm going to do is I'm going to split my piece of paper here, or, well, it looks like a piece of paper, but I guess it's the iPad, into two parts. And of course, this is all like very pedantic, but I mean, whatever way you want to solve the recurrence relation, as long as it works, you know, you want to do induction, you want to do the other way from the end to the beginning, whatever you want to do is good as long as you get the right answer. I don't care which way you do it, even if you use Master Theorem. But you know, I'm still going to show you a very, very peculiar way of doing this, because I that's the way that I'm used to doing it. So you don't feel compelled to follow my lead on this if you prefer another method. And this might be the case if you already took like discrete math or those kind of classes where they might go over these things. Okay, so I'm just rewriting the same recurrence relation. Okay, and I'm going to label this as my build solution column, and over here is going to be my sort of scratch area, which is my expand scratch. So really this is like scratch work area on this side, and then the other side is like the legit side. Okay, so what I need to do is, again, since I'm solving it from the top to bottom, if I could find out what t to the n divided by 2 was equal to, if I knew what that was equal to, I'd know the answer. Like if just like out of the clouds opened the light and was like shining and told me like n divided by 2 is equal to 42, you know, just came out of nowhere and said that, that'd be great, because then I'd be like, awesome, I can now just plug it in and solve my recurrence relation right now, like this little second. Unfortunately, no such divine influence is going to come and save us today. So we're going to have to figure out what n divided by 2 is equal to, because that's the recursive term essentially here. Okay, and so that is going to be your goal. And again, we did this before with a simple one, but now we're going to do it here. So how do we expand it? What we need to do is we need to plug in, instead of n, wherever we see an n, we need to plug in n divided by 2. And that way we'll get this term. Okay, so let's actually do the 4n part first because it's a little bit more obvious there. So what I need to do with the 4n is I need to replace that n there. So 4, and then there's the n, with an n divided by 2. That's it. Quote unquote easy. Right? So at least we got that part done. Now as for the other term, the 2's still there, but instead of putting in t n divided by 2, I'm going to erase it here, but instead of putting this, we need to replace this n divided by 2. We still have the 2 part there, but the n part on top, that right there, we need to replace that with an n divided by 2 of its own. So like a real tiny n divided by 2 there. Okay? So n divided by 2 by 2 per se. Okay? That can be rewritten into that, right? N divided by 2 times 1/2, which is equal to n divided by 4. Okay? Hopefully you guys are, I'm going super slow here, but so that I keep track, you know, I keep you following along. Okay, here's where I'm going to do something that you might be like, huh, that's weird, but there's a reason I'm doing it, and that is I am not going to, you know, I could now that I figured this part out, you know, I could totally, and I'm going to copy paste because laziness. I could totally just leave this here as n divided by 4. That would be, I would say, the simplified version of this, if I could write a 4. However, I'm not going to do that. I'm not going to do n divided by 4. I'm actually going to do it as n divided by 2 to the second power. And you might be thinking, why? Like, why would you do that? Like why? Big question, why? Here's the thing. This is the part where, like, we're kind of cheating a little bit ahead. A lot of the times, this recurrence relation stuff is about finding a pattern. In fact, if you ask the people on Discord that took the class last semester, that's like a meme at this point. Like, yeah, so solve these recurrence relations, just find the pattern. That's, of course, harder. You know, it's harder than it sounds. In fact, it actually sounds pretty hard already to find a pattern or something. Whenever somebody tells you to find a pattern, you know that thing is going to be really, really hard. Okay, and I'm just warning you about that. So, because finding patterns is hard, one of the ways that you can try to discover them is by leaving terms not simplified. And one of the things is like leaving things like an exponent left. If it's something like 2 times 2, you should already assume that the fact that I'm multiplying a 2 times a 2 and those two numbers are the same is a sign. So you either want to leave it as 2 times 2 or 2 to the second power. But don't make it a 4 because you might miss the fact that these were originally 2. Okay? So you'll see that this actually is going to come to play. So I'm going to leave it like that intentionally. Okay? Similarly here on the other side, I run into another situation. The term in here, this term here, I cannot simplify the 2 outside from here because this is a function, okay? It's very important to understand this is like a function, like a program function, okay? So I cannot just like jank things out of here because these numbers could be processed in this function in a way that I don't know what's happening, okay? So I can't simplify the 2 here with the 2 here. That I can't do. Over here, however, is no function. Oh, by the way, I forgot a plus because there's a plus. But there's no function here. So I could simplify this into 2n. I could do that, okay? I could simplify that. But I'm not going to do it yet either. Because again, simplifying in this case is not always the right answer because simplifying will hide the pattern, okay? Now it makes sense because emphasize logs. Cool. All right. Yeah, it does. It does like emphasize logs when you leave the divisions like that. You're right. And logs usually involve powers. So yeah, if you suspect there might be logs in a solution, then yes, you want to leave those divisions like that. Okay. So anyways, we accomplished our task. We have figured out what this is equal to. Of course, there's still a recurrence relation inside of it. There's still like the function there, but that's okay. That's okay. So now let's go ahead and plug the scratch work into the area here. So our goal is to plug in, I can use colors, to plug it in right there. So how we're going to achieve that is I'm just going to say this is equal to, and then I'm going to put a 2 and I put a big gap like that. And I start zooming in so I don't run out of space probably. And then I'm going to put my plus 4n here. Okay. So I got everything from the, all I did is I copied the top line to the bottom with the exception of not plugging in the t part, the tn, right now it's tn divided by 2, right? I'm not plugging in that in. Why? Because instead of putting the tn divided by 2, I'm going to put in what I just did here. In fact, I'm literally going to copy and paste it. Just for special effect. So I'm taking that and I'm putting it there, except I got to shrink it so it fits. There we go. Okay? So that is what I have done. Okay, cool. Next step, simplification. This time we do want to simplify some stuff. But again, we got to be very careful not to oversimplify and lose sight of the big picture. Okay, so first of all, we can get rid of the square brackets because they're just kind of there to kind of tell you where to plug things in. What we cannot get rid of is, again, the term that's kind of special here is this one. This one we can't touch. Like we can't touch in there because the t is a function again. Okay, it's like, to give you an example, imagine that you were writing some pseudocode and it was or just a line of code in C++ that was something like cout 2 foo 5, like that. Okay, you can't just like multiply 2 times 5. This is literally a function. This function might do like magic, and then it'll probably return more magic, and then you multiply that magic times 2, and then you get whatever you're couting. But you can't just jump in there and multiply them. Okay, so that's just something that I commonly find people kind of doing, thinking that they can just kind of go in. Like there's the math properties that we were talking about with logarithms and stuff, but this is not a number. This is a function. Okay, so that's what we can't touch, that guy. What we can touch though is everything else. So we got the 2 times 2 here. Again, we don't just want to make it a 4, so I'm just going to make it 2 to this power of 2, because otherwise I'm going to get a bunch of 2's here, and the exponent is more compressed. But I don't want to simplify it. Again, I can't touch this part, so I'm just going to leave it as is, like that. And then the leftover that I got is I got plus 4 n divided by 2 plus 4n. Sorry, I forgot to multiply. I forgot to multiply. Technically speaking, the brackets do have a tiny purpose there, which is multiplication, right? I got to multiply 2 times both terms here. I got to multiply it times. So like this 2 here is being multiplied, right, for this whole thing. So I kind of misled you there, because technically speaking, this 2 here has to be multiplied times this term, which is how we got the 2 squared. But then it also has to be multiplied times this guy over here, right? Right? Because like if I have 2ab is the same thing as 2a plus 2b, right? So I got to make sure I multiply the 2 times both sides. So yeah, I almost screwed that up there. But yeah, so anyways, you know, I'm just gonna put parentheses like, no, I'll just do it here. I just have to, I usually just have to start zooming in to be able to make it fit. This is where I wish I was in a classroom with a big board. So let's make that a little bit small. And then now we got a plus. And then 2 times that. Okay, there we go. Okay, so now we got the 2 in there. So now I could leave it like this. This is as far as I could go. But I'm gonna slightly simplify it because I see that I have a 4n here, and you can see that if I multiply the 2 times the 4n divided by 2, the 2's cancel, right? I can cancel out these 2's. Let me like cross them out. So like this guy's gonna cancel with this guy. Essentially, I will be left with 2 to the power of 2 t n divided by 2 to the power of 2 plus 4n plus 4n. You see that? If you did, let me do it here outside. So we have basically this here, and so essentially this can be rewritten into 4 times 2 times n times 1/2. And again, this and this cancel, right? So that's pretty much what I'm doing. I'm sure you see that. Okay. So, cool. I'm one step closer to my solution. In fact, closer than that, because I went from like n divided by 2, as you said quite a while ago, n divided by 4, right? However, I still haven't really had enough to see a pattern yet. So I'm going to go ahead and do it a few more times, okay? So let us go ahead and now go to the next step, which is to figure out what t to the n divided by 4 is equal to. So now I got to figure out, so go back to my scratch side. I got to figure out what n divided by 2 to the second power, or 2 to the 4th, or n divided by 4 is equal to. How do I do that? I look at my original recurrence relation. My original recurrence relation is just basically 2t n divided by 2 plus 4n. So 2t n divided by 2 plus 4n. Okay, except n here is now n divided by 4, right? So in this case, this is now going to be 2 squared, which is basically what this term is here. And for this one, it's actually going to be n divided by 2 squared times 1/2, because this is usually n divided by 2, right? So that can be changed into just saying n times 1/2. And since the n here is being replaced by that, then essentially we get this. So that can be put together as n2 to the divided 2 to the 3rd power. Do you guys see that? This is the important part that you got to make sure that you're following along. How I got this term right there. How I got that n divided by 2 to the 3rd power. Again, what I'm doing is I am looking at my original recurrence relation. It says 2t n divided by 2 plus 4n. I am plugging in n. I am replacing the n's. So I'm replacing this n and this n with what I see here. So I am replacing it with n2 squared, okay, or n divided by 4. But again, I'm keeping it like this because I want to see the pattern, right? That's all I'm doing. I will literally visually do it for you. I am replacing this n right here with this term. I'll just shrink it a little bit. Oh my God, it transcended to another dimension. Oh, here we go. Like that. That's literally what I'm doing. And similarly here with the n over here. So like this guy, I'm replacing with this guy. Okay? That's all I'm doing. And of course, then this n divided by 2 squared divided by 2 can be rewritten as I did earlier into n divided by 2 to the cubed. Okay? So that's all I'm doing there. Okay? So I think after showing you that, you see it now. Okay? I'll leave that there because that might be useful for you guys to have. I just don't want you to get confused. Cool. So that is how I have now my next term. So now that I have this term over here, I can go ahead and plug it into my build side, or this side, my build side, okay? So that is what I'm going to do next. I'm going to go ahead and take this part and replace it with this part, okay? So let us proceed to do that. First, I'm going to write all my stuff out, leave a space in there so I can copy paste. And then I got my 2 4n's. Okay, my I'm starting to do some lamp reclamation on the other side. Okay, so now I'm literally going to copy paste again. So on one side, I don't like the fact that I don't have a board, but on the other side, I love that I can copy paste because I think it's more visually understanding that like this, what I'm doing is I'm taking this, which is equal to this, and then just plugging it in there. That visual aid actually is kind of cool. So pros and cons. I think I just need to get like a 20-inch tablet or something. So, okay. Cool. So I went ahead and did that. So let's go ahead and simplify a little bit. Again, replace those with parentheses. So right now we have 2t cubed. Oh, that's crappy parentheses. Plus 4 and divided by 2 squared. And then the 4 ends. Okay? So let's multiply the 2 to both sides so we don't screw that up or forget that. So on this side is just going to become 2 cubed, t and 2 to the third. And on the other side, we got to be careful because now it's not 2, it's 2 squared while we're multiplying. So really we're doing 2 squared times 4 and divided by 2 squared. And then the 2 plus 4 ends. Okay? Notice again, this is no coincidence. That's the word I was looking for. There's no coincidence that these two cancel again. The pattern is emerging. So that becomes 4n, and then we have our other 2 4n's. Do you see the pattern now? Do you see the light at the end of the tunnel? Look, let's kind of highlight the lines, the important lines here. So let's use a light color, green. So first we started with the original recurrence relation, and then, which is this one. And from there, the next stage, well, after we simplified everything, was this one. And now we are here. Look at them, admire them, embrace them, embrace the meta of recurrence relations. We have Tn is equal to 2Tn divided by 2 plus 4n. So first of all, what can you tell me about the 4n's? Every step of the way, what's happening with the 4n? And then what is happening with the value inside of the t part of the recurrence? So I'll let you guys on chat. I'm guessing there's a delay, so I'll tell you. So, oh, here we go. An additional 4n for each instance of the recursion. That is indeed correct. We are indeed getting an extra term of 4n. So first we have started with 1 4n, then we added with 2 4n's. Now we're at 3 4n's, and I think you could put money that the next term would have 4 4n's, and so on. And then for the recurrence part, we started with n divided by 2, and then n divided by 4, and then n divided by 8, right? Because it's 2 to the first, 2 to the second, to the third. So you can see that every term we are getting an extra divided by 2 on the recurrence part, and then the 4n's we're getting an extra 4n. Okay? So let us go ahead and rewrite the 4n's into a way that kind of follows that pattern. So we could probably rewrite this and say, oh, and also the 2 part in the beginning, right? We start with 2, then we started with 2 squared, and now 2 cubed, so that's also growing. And divided by 2 cubed. And then let's go ahead and put this in the form of 3 4n, like that, okay? So, just to show you one more step, you already have it there, indeed, what we're gonna get to, but the next step, and I'm not gonna fully do it, but I'll just show you what it would have been, is you would have figured out what, and I guess I'll do it up here because, or here I can just zoom in hard, is to solve what t and 2 cubed would be equal to. And that, of course, you know, I'll zoom in. It's going to be really tiny, but it's okay. That would be equal to 2t, 2 to the 4th, plus 4n divided by 2 to the 3rd. Okay? And then you would have plugged it in, and you can agree with me that we would have ended up with 2 to the 4th t n divided by 2 to the 4th plus 4n, right? And so basically, as your colleague correctly said, we can figure out that the general sort of pattern that this is following, and again, this is the tricky part, is that this is going 2 to the I, t, n divided by 2 to the I again, plus I times 4n. So how did I do this magic here? Look at the powers. The powers are going by ones, right, on each ones. And then the number here, the multiplier of the 4n's is increasing by 1. So I'm just saying the I represents the nth, or the ith, yeah, the ith iteration of this that we're doing. This is the fourth one, so we would plug it in. So using this, if I was equal to 5, I'd get the next term, which would be 2 to the 5th t n divided by 2 to the 5th plus 5 4n, which indeed would be correct. Okay, so that shows you that this is the proposed solution. Okay, now that you have this sort of proposed solution, you could of course go and do induction, but we're going to keep going what we're doing. Okay, because what we're trying to find at this point is how many times would I need to do this before I reach the base case, right? That's the whole idea of this recurrence relation, is how many times before I stop. Okay, how many times do I have to go to get to my base case, which is to be able to make this inside part be equal t of 1 equals to 4, right? Because I know that's the base case. So how far do I have to go before n divided by 2 to the I becomes that? Well, let's just go ahead and plug it in, because that's what I need to do. I need to make n divided by 2 to the I, because that's what's inside of the t part, right? I need to make this part of this, I gotta convert that to basically be 1, right? Because if it's 1, I know what the answer is, because that's the base case. So I need n over 2 to the I to be equal to 1. That's what I need to solve. What value does I have to be equal to that? Okay? That's the goal. Well, it turns out that if you multiply both sides by 2 to the I, essentially, so if I take times 2 to the I times 2 to the I, that way I can cancel that, then n has to be equal to 2 to the I, right? And that we know has to be what will give me 1, okay? And so if we take the log of this, we can see that I would be equal to that, okay? That's using the logarithm identities. Because if we take the log of both sides, so if we take log 2n equal to log 2 to I, then as we saw, basically I can bring down the exponent. Oh, failed. We'll try that again. I can bring down the exponent here, and then log 2 is just 1, right? So that just disappears. And so that's how I got that, in case you don't remember what we just did earlier, okay? So I get that. So that, what does this mean? This means that this is the value of I that I can plug into this equation up here. If I plug in log n to that I right there, then I will be able to make this become this. And that's good because I know that's my base case, which is 4. Okay? So that's going to get me closer to my goal. So let's go ahead and plug it in then. Let's plug it into the general solution. So let me copy the general solution here. And I know that I has to be equal to log of n. Again, log base 2, okay? So let's just plug it in. Just literally copy and paste it everywhere you see it. So this here, we're going to put log of n. And then down here, we're going to put log of n. And then up here, we're going to put log n. Okay? So we're just basically plugging it in. in all of them, okay? And they're all base 2s, okay? I just really tiny to put the 2 in there, okay? And that's because I already shown you that that is how I get this I, okay? I shown you that what I'm trying to do is I'm plugging in the special case because I know that now this part is guaranteed to become 2 log 2n t of 1 plus log n for n. How did I do this? How did I go from here to here? Because I have shown you up here that n divided by 2i is going to be equal to 1. I have proved you this. And because I have proved you this, I am now plugging it in into my equation to get this. And why am I doing that? Because now I got rid of the sort of the function part of this. And now it's just numbers. In fact, that just becomes a 4, right? Plus log 2n for n. Now this is a multiplication here. It's not inside of the log, okay? In fact, here, let me put parentheses to just make sure you don't get confused there. Okay? I don't want you to think that the 4n is inside the log part. Okay, so now we just gotta simplify this. We're almost done, essentially. So the only scary term, or scary as a point of view, is the 2 to the power of log 2n. But there's nothing to be afraid of that term if you remember the log properties. Because one of the log properties that we covered is, if you have something like this, x log 2y, you can switch the y and the x. So you can basically make x log 2y become y log 2x, okay? Here, let me make a better arrow. You can do that. And so because you can do that, we're going to do that to flip the n of the 2. So essentially, we put that there, and we put that there. Okay? Now that's a lot easier to solve because I know log 2 is just 1, right? So this really just becomes an n. Okay? Basically, the way that you can solve these things is just to have your logs standing by, and if you ever see basically something that looks scary with logs, and you look at your charts of things you can simplify, look at them and see what can I do to just get rid of the weird log terms or any weird term and just make it with simple basic numbers, okay? Sometimes you can't do it, okay? Don't think that you can always simplify things. This, of course, is a pre-manufactured example, of course. But a lot of the times you can progress to get closer to a solution that way, at least a solution that's more plain English kind of thing, okay? So, anyways, going back to what I had up here. So this is the latest one that I had. And now I'm replacing this term with just a single n there. So that looks much nicer already. Let me just rewrite it. 4n plus log 2n times 4n. Okay? So at this point, there's a couple of things that you could do to simplify it. For example, you could take out the 4. Oh wait, there's no plus here. It's a multiplication, isn't it? Oh no, it is a plus, right? Yeah, it's a plus. So you could, I mean, here, let me write it in a nicer looking way. So let me put the 4n in front of the log, and then put the plus 4n like that. Okay, so you could leave it like that. You could also take out the 4 and say n log n plus n. You could also take out the n if you wanted to. 4n log n plus 1. However, I think that the best one of all of these is actually the top one here. Because that's the one that kind of explains more about what the asymptotic complexity of this is. Because I can now say that this belongs, I have to shrink this a little bit to not run out of space. But I can say that that belongs to the asymptotic complexity class of n log n. Yes. Now you might be saying, what about that 4n? The 4n is insignificant compared to the power of the n log n side. So basically, if you were asked to show a certificate for this, you can say something like that. And given the fact that it would be something of the format of Cn log n plus c, something like that. Potentially. You don't need that last c, but at least you need the second c to not run into problems. But yeah, so there you go. That is the entire thing, essentially. At this point, you have solved the recurrence relation, and more importantly, you know what the asymptotic complexity of the problem is. So whatever the code that you create that gave you that recurrence relation was, is going to take n log n time to run, pretty much. And so if you have an algorithm that takes n squared, and then you have this one that takes n log n time, this one's going to be way faster than the n squared one, especially as the n increases. So yeah, that's pretty much it. Any questions about the example? Any clarifications or anything? Cool, cool indeed. So now, as to what code could have given us this recurrent relation? By the way, because I was thinking somebody would ask that. I'm glad you did it, because I have to kind of guess. It would be a code that, well, I mean, the easiest format is just to write the same code recursively. So just like an n that the function call divides it by 2 every time. And then, but the plus 4 part is tricky, so I'm not sure as to what code it would account on that. But the point is that if you were trying to write the recurrence relation for a piece of code and you got that recurrence relation, then you would solve it that way. So, okay. For that same problem, I have one more way of doing it. Do I have that already here by any chance? I have a picture of it. I might be able to copy this picture. And let's show you. Yeah, this will work. So this is a picture of my notes. This is one other way of solving this that I don't really cover, but I just wanted to show it to you. The same problem, exact same problem. This one's called the tree method. I think that's the name of it. The way you do it is you're still trying to come up with that general sort of solution, the 2 to the I power one. And so instead of doing it more like mathematically like I did, here I'm just kind of seeing how it grows and how the n gets divided by 2 every time, as you saw. And then the row sum is what you add in outside of the actual recursion part of the t part, which is always a 4n. So you're always adding up 4n. You kind of see that every time you do this, no matter what happens, if you look at how the equation is made up, you can see that this part is a function that's going to generate more functions, right? As we saw. But every time you're doing this, you're always just adding up 4n, right? So that's how you know that you're always adding up 4n. I mean, now it seems obvious. Maybe back then it didn't, but that's why this method's kind of iffy. But you can see that this is also going to just keep dividing this in halves, which means that one call is going to make 2 and then 4 and then 8 and so on. And so you can see that and then essentially see that this is a 2 to the I part, and then this is going I times that. And so pretty quickly, oh, and then also the multiplier here, the 2, is also going by 1 every time. And so doing this method, you can also come up with the same with the same general solution, which is a 2 to the I times t to the n divided by 2 to the I plus I times 4n. And if you come up with that general solution, then you can do the rest of the math as we did before to come up with the final solution. So just another way. You can read the book or go online and find more about it if you like it. Again, I don't care which method you use, but it is indeed available to you as well. So that's it. Yep. So that pretty much is the entire recurrence relations topic as a whole. The only thing left now is to talk about the Master Theorem. I could talk about it now, but I have to pull up the notes because I think I might be faster if I just pull them up that way. So what I'll do is maybe a little bit of time in the beginning of next class, I will give you a brief overview. It's not going to be the entire thing, because I mean that's like 477, and you take a while learning that, and also you probably learn in math too. But the Master Theorem is a shortcut to doing a lot of this stuff, and so I'll try and go briefly over it. I can't spend too much longer on this because today's the last day that we can really do recurrence relations, but so we don't start falling behind. But I'll try to and sort of throw it in next class, and then we can kind of discuss it. And you can see another way of solving recurrence relation. If not, then you can go and Google it and go on Wikipedia. But yeah, is there any situation where the build and expand method wouldn't work? Absolutely. There's recurrence relations are just differential equations or a subset of them, and so, or yeah, I think it's not, yeah, that way. So there are some recurrence relations that the pattern per se is not anywhere at all visible until you go like super deep, and so there's just no way of easily solving it. See, just like differential equations, again, I keep going referring to that because at the end of the day, some math problems, like, you know, a lot of the times when you take high school math and college math, you kind of think of math as sort of a, you know, you have a problem, you have a defined way of solving this problem, and it'll always give you the result. Kind of like with algorithms, you know, have a defined algorithm that's always going to give you the result. Turns out you can't write, or at least we don't know of any algorithms that are guaranteed to always solve a certain type of problem. Recurrence relations are that way, and differential equations are that way. What may work for one of them will just totally not work for another method. Okay? So the method with the build and expand relies on you discovering a pattern. Otherwise, you'd be building and expanding on for eternity. If you don't see that pattern, or if it's not visible, then it's not going to help you at all. So yes, there are some cases where that pattern is just not visible at all, and you're kind of screwed there. Master Theorem is going to kind of help you out there, but even the Master Theorem is limited in that sense. There's some recurrence relations which just have no easy way. There's no formula you can download and just, or some guideline that you can download and follow to the point and just get the solution. That's why differential equation is like a really hard class, because you got to learn all these weird methods that only work for these specific subsets, like Laplace transforms and all of that. So yeah, I have like PTSD for that class myself. So anyway, that's just kind of, I know it's kind of disappointing, but I mean, decidability, if you look at the last lecture, which I don't know if I'll do the same thing this semester, but the last lecture last semester in 302, we talked about like decidability and all these things. There are some problems in computer science and in math that are unsolvable. And that's just kind of it. We can't solve them. And it's not because we don't know how to, but because, like, theoretically speaking, they're unsolvable unless we like prove like P versus NP and that kind of thing. So yeah, that's kind of the way it is. So yeah. Anything else? So the next thing we're going to talk about is going to be, you already had an assignment, assignment 1 that talked about vectors. So I don't really need to talk much about vectors, other than I want to make sure that you guys understand that vectors are arrays. And so they're dynamically allocated arrays. They're not linked lists, and they are resized on demand. And so what that means is that internally, when you're pushing something into a vector by using the pushback function, it checks to see if there's space, and if there's no space, it will actually make a brand new array, copy all the elements over, and the new arrays are obviously bigger, and then just put it at the end. So ultimately, vectors are nothing more than glorified arrays, dynamically allocated arrays. But that is not to talk down upon them, because they're amazing. Like, they make your life 10 times easier. And I highly encourage you to use vectors all the time. Learning arrays and learning dynamic arrays has a purpose in 202, but like, let's be realistic now. We've moved on past that. Now we are trying to just get things going on code. So feel free to use vectors unless I specifically state not to use them. So that's pretty much it about vectors. However, vectors have the same disadvantages that arrays have. And that is that you have to resize at some point. It's just happening behind the scenes and you don't see it. But it is happening, and it does slow things down. Similarly, there are advantages to vectors that something like a linked list wouldn't have. And that is that you're able to access any element of a vector immediately because it's an array. So you can just get the 6th element like right now, then, bam, you got it, right? And by the way, vectors, again, you are able to enter in the middle of a list with a vector, but internally there's some magic going on to be able to like shift things around, you know, like part the seas kind of thing. And I don't know exactly the internals of how that's implemented. I just know that it's an array. If you want to do a 2D array with vectors, is it easy to do vectors within vectors? That's what I've done in myself in the past. Is yes, just basically make a vector within a vector. There's probably smart, and I think you can even, if you do it that way, the array access operator will work still, if you do it right. So that's just like icing on the cake, because then you can still be like that, and it'll work. So I think so, if I recall. I think I did that at some point. What assignment did I do it on? I think it was like a 202 assignment. I can't remember. Maybe it might have been a 302 assignment. Yeah, I think it might have been a 302 assignment. It might have been like the CSGO assignment, the CSVO. So, yeah. So, anyways, that's the little talk on vectors. Next class, the main focus, after I briefly go over the Master Theorem, is going to be to talk about linked lists and arrays and the pros and the cons of that. And we'll go pretty quickly over that. So, we might even start into sorting as well. Okay? The next assignment that you're going to have to do will involve coding and linked lists and dynamically allocated arrays and vectors, because I want to make sure you guys are good with those. So you will be taking previous assignment and converting it to using a linked list, and that'll be fun. So stats, you know, I'll go ahead and publish that probably on Wednesday. Is the next assignment due next week or the week after? I'll probably make it due next Wednesday. We'll find out. As for the assignment that's due like tomorrow, that's the recurrence relations. You should be totally good to be able to do that. So yes. And also you will get a worksheet, which will be kind of like a study guide for the test. It'll be assignment, but it'll be like the questions you get on the test. That I'll be posting at some point. I think the first worksheet covers all the way until linked lists. So when we finish that, I'll post it, and then you'll have that as well. So that is what is on the future for us. But for now, I think that's where I will stop. So, yes. Anything else? Any questions before we sign off? You're welcome. It is my pleasure. Like I said, I really do enjoy this class. And I'm kind of relieved that we finished recurrence relations. Well, almost. But we finished the hard part. For assignment 2, do we submit 2 C++ files, one with the original code and the other with the recursive functions? No, combine it together and just have the code, have the iterative code run first, and then the recursive code. And the caveat with that is that if check it on Sally, and if on Sally it's crashing after a certain number of n values, then make it easily modifiable, either like a command line argument or put a define or something that the grader can easily turn that section of the code on and off, so that they can basically test your iterative version without it sec faulting because of the going out, running out of memory. For the nested loops in assignment 2, should each inner loop have its own recursive function? I'm trying to remember how I did that. I think so. I think you do need to do that. Yes, if I recall. Yeah. Because I don't want loops in the recursive version. The whole point is to show you how recursion can really kill your machines. question about assignment 2. Are we doing the asymptotic complexity for the whole program or for each code section? For each code section, because that I want to make sure that you guys understand that each of the little codes has its own asymptotic complexity. So yes, for each code section, I want the asymptotic complexity, and then I think I make you run the code and count, because what I want you to see, what I want you to get out of the assignment is that what you compute ahead of time to be the asymptotic complexity, like mathematically figure that out. Well, go mathematically. You're just looking at the loop and whatnot. And then you compare that with the experimental measurement, and you want to see that those match. And then you're like, oh, wow, they match. So, like, it's not magic, you know, how to compute that. So that's the whole purpose of that. So I want it for individual pieces of code. For logarithms, if it's base 2, do we need to specify that it's base 2 in the recurrence relation problem? That's a good question. For this class, if you don't put a base, it will the graders and I will always assume that you're talking about base 2. So don't ever worry about having to put base 2. So that's a good thing, I suppose. Yes, we will. If you ever want to use a different base, then yes. But yeah. Yep, you can head off now. We are indeed finished. It is 5:15. But you're going to keep asking questions. I'll be here for a little bit if you guys need, until no more questions come. But yes. So, yeah. I mean, I don't ever write the base 2 thing. I tried doing it today just because we're starting it, but you'll see that I rarely write it. And most people don't write it either. Even when you go online, and it's bad because, like, sometimes, like, you know, if I don't tell you that, people are like, huh, that's weird. Like, what base is it, you know? So yes, you're welcome. I'm glad you guys enjoyed it. Lots of fun stuff coming ahead. All right, guys. Well, if there are no more questions, then that is it. If there are, always feel free to message me, Canvas, Discord, email, whatever you guys want. I will be around. I do have some questions already on Discord. I think they sent me. I think it was a different class, but I took a nap right before the class, so I haven't answered them. So I'll go check that soon. But all right then. I will see you guys on Wednesday for the next class. So take care, stay safe, and have a great day, guys.